Okay, so it's a pleasure to introduce Vlad Bally from Université Gustave Eiffel, who's going to talk about the CLT and the number of roots of trigonometric polynomials.
So I knew Jean Bertrand because we are here for this. I knew Jean Bertrand in '92 when I arrived in Laboratoire de Probabilité. And so I entered in the couloir 45-46 and I pushed the second door on the left-hand side. And there was an office where was Sylvie, Animier, and Jean. And we got friends immediately. And what is amazing is that after almost 30 years, we are as close as in the beginning. And so this is the reason for which I am nowadays here, and I am honored and pleased to speak in this extraordinary conference in honor of Jean. Okay, so speaking about Jean, one cannot avoid to speak about Mexico because of his, all of you know about his love of this country. And Maria Emilia has already mentioned the fact that in '98, Jean and myself, we have gave a course in Guanajuato. I do not remember the topic of my course, but I remember very well that Jean and myself, we was every evening on the place between the hotel and the church taking margaritas. This was what remains for me for this. And afterwards, Maria Emilia was so kind to give to Jean his car, her car, and we make a tour in Mexico, in Morelia, Pátzcuaro, and so on. And this is an extraordinary privilege to be in a country guided by someone who loves this country. And Mexico is really a beautiful country, almost as beautiful as Romania. So, okay, this is the reason for which I am here. And this is the point that it works. Yes, I will speak about the central limit theorem. And I'm really sorry because it's completely out from the mainstream of this conference. But as I push the door, the second door on the left in this moment, this is why I'm here with this subject. So I will speak about convergence in the central limit theorem in distribution norms. I will explain in a moment what the distribution norms means. And this is the work in collaborations with Lucia Caramelino from the University Tor Vergata and Guillaume Poli from the University of Rennes. So, so this is really the central limit theorem. I mean, we take some independent random variables, RD valued independent random variables, which are centered and which have covariance matrix identity. And then the central limit theorem says that 1 over square root of n sum from e to n of xi converges in low to the Gaussian distribution. This means that for any function which is continuous and bounded, you have test function continuous bounded, you have this convergence. This is a classical central limit theorem. And in the year 50, it becomes of interest to see if one can have here convergence in total variation, which means that we can have this convergence for a function phi, which is measurable and bounded. And it was a big activity in this moment. For example, this function phi may be an indicator of a set. It was a big activity for starting with a theorem, very nice theorem of Rao, who proves that if a set A is convex, then you have this convergence. And then it was, so we have seen some efforts of Bhattacharya and Rao to characterize the boundary of the set A in order to be able to have this convergence. At a certain moment, one got the impression that this will work every time, but it's not the case. And so it was a theorem of Prokhorov who completely clarified this problem, because he gave, Prokhorov succeeded to give necessary and sufficient conditions in order to be able to have convergence in total variation is the central limit theorem. What this theorem told is that if you have a general law, if xi is coming on, have a general law, you will not be able to prove convergence in, you do not have convergence in total variation. For example, if xi are some Bernoulli random variables, you do not have such a convergence in total variation. And let us read a little bit what he says, that convergence in total variation boils to have some condition on the law of the xi. And he says there exists an M, then you make packages of order M. And if you have packages over M, these packages have a law which have at least a small absolute continuous part. And if you look a little bit, make one more step, if you put two packages, one with another, with some two packages, and Z is Y1 plus Y2, then you have a convolution which means that the absolute continuous part has a density which is G, which is continuous, So what I retain, from this theorem is that the random variables at hand, essentially, after making some packages, essentially have to have an absolute continuous part with continuous density. And so if you want to discuss total variation distance for this, you have to think to such laws for the random variables of hand, which have this part absolute continuous. Okay. But you know, if you have if you have so the law of Z is of this form. So we have a small part here where you have some density, and then you may have some other parts I do not know. And so this is a G. This is a G. But if you have something which has a density, this is strictly positive, has to be strictly positive, at least on one small set. And then you can put here a box, which is below. And also, if you can, for technical reasons, I do not like boxes like this. I would like that this box has some regularity. And so I smooth a little bit the box. But even if I smooth it, it remains inside the part of density. And then, the idea is to split the random variable Z in two parts. One part will be the one which has this smooth density, and the other part is all the other things. Of course, this, and then so you have these two parts. Of course, they are not of mass 1 because they have splitting, but you renormalize in order to get a random variable of this density, which is renormalized, and the other one. And then what you are doing is that you throw a coin, and you choose the regular part, or you choose the other part, the remaining part, and you throw a coin in order to do this, and the coin you throw it with a percentage of the mass we have here and the other mass. So it's a very simple and clear way to construct Z as a sum of Xi times V plus 1 minus Xi times U. Xi represents the coin you throw with a percentage on one of another. V is a part which is smooth. V is a part which has a smooth density. And U is the remaining part. Okay? And so this is a splitting method that I use in the following. And so what happens is that nowadays I do no more work with Z1, Z2, Zn, the copies, but I will work with Xi I Vi plus 1 minus Xi I Ui. And so is the sum, the Sn is the sum of these guys. And what I hope is that I can do some integration by parts techniques based on V1, V2, Vn. So on the parts which are regular here, we have regular density, and that this integration by parts technique would help me to replace to regularize the functions f, which normally the test functions, which normally are only bounded and measurable. And now, so what I want to, the first thing that I do is to give a new proof of the theorem of the part of the theorem of Prokhorov. So I will prove that taking a function f, which is measurable and bounded, I have expectation of f of Sn minus expectation of f gamma dx. Gamma is a normal distribution, is less than c over square root of n, norm of f infinite. So the first thing is that we find out the same result that of the result of Prokhorov. But what is interesting, what is the subject of my talk today, was that we can go further, and instead of looking just to test function f, I can look to derivatives of the function f. So I take a multi-index alpha of length q, and I look to d alpha f, the derivative corresponding to alpha of f, and I look to this difference with derivatives of test functions. And what we prove that this difference is less than c over square root of n norm of f infinite multiplied by a power minus cn norm f q infinite. The norm f q infinite means that there is a norm of the subnorm of all the derivatives up to q. If this term was not here, was not here, this is what I called convergence in distribution norms, because I am able to have the convergence for derivatives controlled by f norm f infinite. So this would be the convergence in distribution norms. But as you see here, we failed to obtain convergence in distribution norm because we have this supplementary term here. Okay, the question is, there are two questions. One question is it possible to throw out this supplementary term? And the result is, the answer is no. Why this supplementary term appears? As I told before, I split each random variables xi I vi plus 1 minus xi ui. And so essentially, what you have expectation of d alpha f. And here you have sum over e equal to 1 to n, 1 over square root of n, of course, psi I vi plus 1 minus psi I ui. You have this quantity. And what you hope is that the vi have a very smooth density, and they have something as a regularization effect, which comes as you have convolution. If you have a convolution with a regular function, you get a regularization effect. And so the regularization effect will come from the VIs. But if you have bad luck, you throw your coin, and all the time you obtain psi I equal to 0 for each I. And if all the psi I are 0, you can do nothing, because you just have the Bernoulli random variables which have no regularity.
Sorry, what is your alpha?
Which alpha? It's the derivative of order alpha. Alpha is a multi-index, and so you can just take f prime, for example, a derivative, and you want to regularize this derivative. If you have the VI, you have a chance to regularize. If you have no VI, you have no chance to regularize, and even the, say, Prokhorov theorem says that it doesn't work. because the convergence in this case, because you just will have something like this, which have not an absolute continuous path. This doesn't work. So there is no chance. There is no chance to. Oh, pardon. No. There is no chance to put out this term because there is a bad region where he is there. On the other hand, you know that the probability that if you have some random variables 0, 1, the probability that they are all of them 0 is very, very small. It's exponentially small. This is Hoeffding's inequality. And this explains why here you have a term which is exponentially small. And so this is somehow the better result that we can get. Now, the question is such a result, because we have this reminder here, such a result may be interesting or not. I hope I will convince you that even like this, it has been maybe interesting, but before I make some comments. So a first way to use such a result is that instead of using a test function, a derivative of a test function, which is very irregular here, I will regularize this by convolution, for example, by convolution with a Gaussian random variable. And I compare these terms, so I do not look directly to the very irregular function, but to a regularized function. And I have, in this case, when I have regularized here a little bit, I will get the inequality without this parasite term. And what is interesting is that the regularization is a very thin regularization. I can regularize with something which is of a variance very close to 1. So it's the regularization is done with a with a function which is like this, very steep epsilon and very steep approximation of the Dirac function. So this is a way to get around the difficulty of having here this parasite term. And also we succeed to have, under stronger hypothesis, we have a real convergence in distribution norms. Namely, if I think that Zi, the random variables which appear in the central limit theorem, have a density, and not only a big part of density, but here they have a real density, and if this density is one-time differentiable in one sense, then Sn will have a density, the sum will have a density itself, and in this case, the density of Sn converges to the Gaussian density, really in distribution norms. But this is a condition which is much more demanding because I have much more regularity on the law of the random variables. So say this is a central result that we have obtained about central limit theorem, but we also have obtained some extensions. For example, Zi are not identically distributed. This is one point, and the other point is that we have adjoint expansions. This means that if instead of here we obtain 1 over square root of n. If we want to obtain 1 over square over nk plus 1 over 2, this may be done by adjoint expansions. This means that you do not converge to gamma, but you converge to gamma with a polynomial in front of gamma, with coefficients theta I, which are computed using Hermite polynomials. It's important in what I will speak about in a moment. It is important that these coefficients theta I may be computed in a complicated but explicit way. So we have a real control, explicit control about who are these theta I's. Of course, this type of theorem, the adjoint expansion, is completely classical. What is new here is once again that we work with derivative of functions f, and so to something which is rather irregular as this function. This is new, and not the adjoint expansion itself. And of course, we have still this reminder term which is there. So this is a result in the result of our central limit theorem. And yes. And so it is a nice application of these results. Using this type of result on central limit theorem, we are able to discuss the following problems: the number of roots of trigonometric polynomials. This domain trigonometric polynomials and zeros of trigonometric polynomials is a subject which was proposed by Guillaume Pauly, and he is him who is really the specialist and controls ideas which comes on therein. So what is going on? It doesn't talk no more. Yeah. I consider P and T of y being a trigonometric polynomial. So it's 1 over square root of n, sum from k to 1 to n, yk1 cos of ktn, yk2 sin of ktn. And so this is a function of t in the sense that we have t here and t here. And it has random coefficients which are yk1 and yk2. So this is a trigonometric polynomial with random coefficients. And the quantity of interest is n and y, which is the number of zeros. The number of t is 0 and p, such that p and ty is equal to 0. Is the number of roots of this trigonometric polynomial in 0 and pi. This is object which will be of interest in the remaining of my talk. So there is a result which is known, which is the following, that 1 over n expectation of n and g is equal to converges to 1 over 3. G, when I put g here, this means that I put the coefficients which are standard normal. So if you have coefficients which are standard normal, it is proved in the literature that 1 over n expectation of the expected number of roots converges to 1 over square root of 3. And what we have proved ourselves is that we can replace g by y. So we can put here, instead of standard Gaussian random variables, we can put independent random variables which verify our splitting condition, and we get the same result. So this is an invariance principle that we obtain for the expected numbers. And I will prove this in 2 minutes, because actually it's very, very simple and direct consequence of what we have done before. And in order to be able to touch to the problem of number of roots of zeros of some function, there is a classical way to attack this problem, and this is Cox-Rice lemma. This Cox-Rice lemma is a lemma which concerns completely general deterministic functions. If we have a function f on an interval 0a with a real function which is differentiable, and you ask the following non-degeneracy condition in some sense, that modulus of ft plus modulus of f prime t is larger than a constant, uniformly, strictly positive, uniformly with respect to t. So you have a function which has this non-degeneracy condition. And if you have this, then the number of zeros of f on the interval 0a, number of zeros, may be computed as the limit as delta goes to 0, integral from 0 to a, f prime modulus of f prime of t, and here you have such as an occupation time 1 over 2 delta, indicator function of ft less than delta dt. So this appears as an occupation time, but you integrate in this small set, you integrate the derivative of f. So this is a nice and rather simple to prove, analyze this result. And actually, even you have not a limit delta tends to 0, if delta is sufficiently large, you have they are even equal each other. So this is the way to attack the problem of the numbers of zeros. And what we are doing is the following thing. So we will use the central limit theorem in dimension 2. The first component S1 of T is a number of, is our initial polynomial, trigonometric polynomial I speak about. And because in the Cock-Rice formula appears the derivatives of P and T of Y, the second component will be these derivatives. And you compute these derivatives 1 over square root of n, k sum to k1 to n, k over n, y2k cos of kt minus y1k sin of k t over n. And so we want to use the central limit theorem for this couple.
Vlad?
Wait.
Sorry to interrupt here. There's a question from Dan Christian, actually, who asks if the variable zi's can be exchangeable instead of independent.
Answer, no.
Answer is no.
I do not know. No, the answer is I do not know.
Oh, do not know.
No, but
Okay.
I do not know. It's a little bit different.
Okay,
Yeah.
thanks.
So here what I need is to be able to use the central limit theorem. Now coming back to the central limit theorem, I do not know. So I want to use the central limit theorem here. And so the number of zeros, according to Cock-Rice formula, is limited delta tends to 0, integral from 0 to np, the derivatives of this function, which is a function I have to take as a test function. So you recall that in the Cock-Rice formula, you have here this guy, the occupation time. This guy is something like this. Here you have delta. Here you have 1 over delta. And so you have, this is the thing on which you have S1. And I want to give this as a derivative. And this is the derivative of the following thing. You have the heavy side. You take the heavy side here. This is the heavy side regularized with delta. And this one is the derivative of this. And so the function that I have to use in order to, the function which I have to use in order to realize this thing is the following one, is for x2, you have just the modulus. And for x1, you have a regularization of the heavy side of the indicator function. And then if you derivate this function with respect to the first argument, then you get x2 and then delta 0 of x1. And so it is exactly the other one. So what Cock-Rice lemma says that the number of zeros is the limit of the first derivative of phi delta Sn1, Sn2 dt. This is the way in which the Cock-Rice formula works. And you have to take here expectation. So expectation, which comes inside. And the way in which we use the central limit theorem is that we know that as n goes to infinite, the expectation of this function computed with general y gives the expectation is the same thing as we put instead that y, we put g, Gaussian random variables. So here appears the invariance principle. Here appears the invariance principle. And we have 1 over n here. And you see, we have, this is important maybe to say, 1 over n integral from 0 to np. And you have here some quantity which depends on y minus expectation, something which depends on g. yn, gn, say. You know that this goes to 0 is the central limit theorem will tell this. Here you have 1 over n, and so everything is done. So the proof is really very simple, a complete immediate consequence of the central limit theorem. On the other hand, what I wanted to say is that one can see here that this makes sense to use derivatives of test functions, because it's a derivative which allows me to work instead of working, which allows me to work with such steep approximations of the Dirac functions, because it is a derivative of someone. So this is a motivation in order to consider the central limit theorem for test functions which are derivatives, even if we have some delta here. I mean, it's not the real measurable function, the real indicator function, but it is some regularized indicator function. This is the case here. So this is the first result, but it's not really the interesting result. So the interesting result, much more challenging, is about the variance. So you take the number of zeros, and you take the variance of the numbers of zeros as n tends to infinite. And there is a result which is known in the literature, that the variance of the number of zeros is also of order 1 over n, and the convergence 1 over n variance of ng converges to a constant Cg, which is of order of 0.56. So this is what is known as a result in the literature. What we have done ourselves is to look to the invariance principle to replace G by Y. So instead of taking Gaussian coefficients, we take general coefficients which verify our hypothesis. And what we proved is something like this: 1 over n, the variance of the number of zeros with coefficients which are not Gaussian, converges to C of G, so the same constant as here. But there is a remaining term, which is exactly this one, which depends on the force moment, of the coefficients that I put there. In the case of the Gaussian case, the expectation of the force moment of the standard normal is 3, and so this disappears. But in general, this will depend on the third moment of the coefficient, of the random variable at hand. And so in some sense is non-universality because it depends on the law. So this result is much more involved. The proof of this result is much more involved than the proof of the previous one, because you see, when you have to look to a variance, in a variance appears squares. You have random variable squared. And on the square, you have to look, you have a square, you cut it into simplexes, and you have to look to one simplex and the other simplex and some classical standard calculations. So shows that if you want to look to the variance, you have 1 over n variance is 1 over n integral from 0 to kn dt, integral from 0 to k pi n ds. And then you have the functions that I put before, computed with Sn t of y, multiplied by the same function Sn s of y. So after small computations, you arrive to say that, and this formula says that the variance will be obtained as the limit as delta tends to 0 of such a quantity. Why such a quantity is more complicated, more difficult to handle than the first ones? The first thing is, so what you have to do, what you have to do is to use now the central limit theorem for the couple Sn(t) of y as Sn s of y. So we will use the central limit theorem in dimension 4 for this couple. Why this is a little bit tricky? It is really tricky for two reasons. There is a technical problem which concerns the diagonal, S equal to T. You see, if S equal to T, then you have the same thing here, and so you are in dimension 4, but you have a random variable, which is a vector, which is degenerated. And so this will not work. So there is a technical issue to take out a small part around the diagonal and to deal with all these things. So this is a technical problem. But there is something which is more, even more tricky, is the fact that here you have 1 over n, and here you have 0n, 0n. So you have 1 over n multiplied by n2. So we have n. So what I mean is the following thing. What I have to do, I have to use the central limit theorem in order to replace this with y replaced by g, with y replaced by g. So the expectation of this with y has to be replaced by the expectation of this with g. When I replace one with another, there will be an error. But nowadays, the error will be multiplied up with n. So we will have, when we have 1 over n, integral from 0 to n pi, integral to n pi, here will be something, an error n ts dt ds, an error, and this error is because n. And so the accuracy of this approximation has to be more than n. So here there will be something of more detailed to be done. And if you use, I wanted to use the central limit theorem for this couple, but if I use the central limit theorem for this couple, I will not be able to get sufficiently accurate estimates of the difference inside. And so this is why I have to use edgeless expansions, and even edgeless expansion which are pushed to order 3. I think out there 4, but it's false, I think. It's to order 3 in order to be able to obtain a sufficiently accurate estimate of the error of replacing here y with g. Yes. So maybe it was not clear when I say that I use central limit theorem, I do not use central limit theorem in order to obtain at the end the Gaussian random variables. I use central limit theorem in order to replace the coefficients which are general with coefficients which are Gaussian. At the limit, there may be a Gaussian random variable, but it's not my problem is to replace the one with the others. And so to look to the error about this thing here. So I do not go further in details here, because here is very important the fact that I told you in the beginning that in the central limit, in the edgeless expansion, I have an explicit expression of the weights, because here you will have some specific computations which lead you to estimate the error. And also you see here that you go up to order 3 of edgeless, and the computations are sufficiently precise in order to take out the difference which appears between one thing and another thing at this level. So you have to do things in a rather accurate way. Okay. So this is the applications of our result. I will say just a few words about the integration by parts techniques that one has to use in order to get this regularization. Actually, they are inspired from Malevin calculus, but of course here we are in a finite dimensional case because we have just n random variables, and we have not Gaussian random variables because there are these random variables which are small. But anyway, we use some techniques and some things from this Malevin calculus, and this is important because the following thing: if you put some differential operators, even if you are in the case finite dimensional case n equal to 1000, if you put bad operators, when you pass to the limit with n to infinite, this will blow up. If you put the good operators, they boil well together. This is why we take the operators which are inspired from this calculus. And so this is a rather trivial. So we look to functional f with our functions of ci vi 1 minus ci ui equal to 1 to n. In our case, this was the sum, but we look to such functionals, which is a vi, which have densities. And then we define dk of f, so the derivative k of f to be the derivative of f with respect to vk. And when you have such a derivative, you have to go take out some ck, which appears from here when you derivate. And so this is a derivative operator. And then we prove, we obtain immediately duality formula expectation of df dg, sum over k equal to 1 to n a dk f dk g. It's equal to expectation of f lg. L is the Ornstein-Uhlenbeck operator, where L is defined in an explicit way here. What we are doing in order to go from here to here is just an integration by parts, completely elementary integration by parts. And this completely elementary integration by parts will make appear the logarithmic derivative of the densities of V. So you verify this guy, this duality formula. And also you, you define the covariance matrix for a vector to be the scalar product of dfi dfj, and this is the so-called Mayavan covariance matrix. And in order to put to use integration by parts with this technique and with these formulas, what you want to need is a random variable you have here is non-degenerated in the sense that the determinant of sigma f of this matrix is non-null. Or what you see is what I was telling in the beginning, is that actually you have some accidents. If all that ci are 0, then there is no, then the derivatives themselves are 0, and so the sigma f is 0, and so you are in the best position. So this is a moment when it appears in a quantitative way the fact that you can be in an accident position, in a bad position. But as I told, Hofding inequality says that you have small chances to be in this bad position, and then you can define, realize the regularization lemma and put the machinery of integration by parts work and obtain the result. Oh, I finished plus vite. Merci.
Thank you very much, Vlad. Are there questions?
Can I ask a question?
On the result, on the number of zeros of your random polynomials. So the estimation that you got on the first moment and the variance are sufficient to get a law of large numbers. So with a convergence to 1 over root 3. But do you have a central limit theorem? I mean, you showed that the variance converges.
Yes.
Do you know that there is a central limit theorem once you subtract and
this quantity?
yeah.
No, I do not know. No, I do not know. We have stopped here. I mean, somehow, if you want, Guillaume continues to work in this field, and maybe himself has some new results in his field. But myself, I have not continued in this sense. I think is much more involved. Already at the level of the variance, you have this problem of the accuracy of the error, which we dealt with up to a certain moment, but then we stopped.
Thank you. Other questions? So there is a question in the chat.
Nathanael, do you want to unmute yourself?
Yes. Salut Vlad. Hi. I just missed something, probably a stupid question, but just to be sure I was understanding well. The limit of the variance you said it was a constancy of J, which is 0.56 plus some quantity, but the sum should be positive. And I don't see why in the assumptions on Y1.
Yes. Actually, someone has asked me once again this question, and yes, this quantity has to be positive and is positive, but in this moment I miss the argument. I have to think a little bit why, but once time I have thought about why this quantity 0.56 minus this second quantity remains positive, and it remains positive. But in this moment, I have not the argument in my head. But your question is completely right. But and the answer is yes. But I can
because it shouldn't be an arbitrary variable, random variable y1. It has.
Y1 is not completely arbitrary. So it has moments up to order 4, of course, but also it has this property of having a part which is absolutely continuous. So you cannot take a constant, for example.
Yes, it would be
this is good news. Good news. Yes, you cannot take a constant, for example. But really, there is an argument which tells to you why this quantity remains positive. But in this moment, I do not have it in my mind. But,
and what are the list of assumptions that that Y1 has to check, except to have moments of order 4 and Hello. Okay. Oui. Vous m'entendez plus?
Si, on t'entend.
Ah si, d'accord, ok. Bon, bah ok.
Tu peux le dire en français.
So I think that Dan has also another question.
Hello.
Just give me 1 sec. Go ahead.
The function phi that is used as a lower bound on the part that where the density is bounded away from 0, you could, I assume, choose different functions to play with.
Yes.
And therefore, you will have many versions of the integration by parts formula for each choice of this function.
Yes.
And I would assume that when you start to differentiate the logarithm of the function, you might be able to find some very convenient functions that will give you some very neat integration by parts formula.
Yes, actually, you are right to say that this cannot be any function. This is an intelligent function. The property of this function is the following. If you take derivatives of this function and you multiply it by the function itself, this remains bounded. So it is a property because when you in the integration by parts formula appear the logarithmic derivative of phi, and in the calculus will appear derivatives of the logarithmic derivative of the function, but you integrate all the time with respect to phi itself because it is a density, and this has to remain bounded. So maybe this is a little bit technical, but you are right to ask if this phi is anything, and it is not anything. It's something which has to be chosen with some good properties, but it is done. It's something of exponential, as you have for regularization of compact sets, you have exponential things, is something of this type. Yeah.
Thank you.
Okay. So let's thank Vlad again. This was the last talk of the day, so let's thank all the speakers again.